G'day, Dr. Carl here, Shirtless of Science, University of Sydney, with some of my University of Sydney colleagues to talk about getting to another star system in only a few decades. Wow, this is the stuff of science fiction. Can I please introduce to the microphone first?
So my name's Professor Peter Tuthill. I work in the School of Physics at the University of Sydney. So I have a whole bunch of things that I do to do with ground-based astronomy, but also space-based astronomy.
And you've had stuff on various spacecraft, including the Just Wonderful Space Telescope.
Yes, indeed, the JWST. I've got a little small piece of hardware flying aboard James Webb. And that's, in fact, the only Australian designed piece of hardware aboard the observatory.
So your sort of area is getting telescopes and looking at the output of the telescopes, bearing in mind a telescope can look at anything from gamma rays to radio waves and infrared and ultraviolet and everything. Is that kind of reasonable, or do you tend to specialise in one part of the band?
I mainly do optical observing, so to an astronomer that's also often extends to the near infrared. So from the infrared through to the visible light part of the spectrum. I guess the special sauce I usually bring to the table is that a lot of the work I do is to do with getting the best possible image. So if you really want a sort of a microscope in space, you want to zoom in and get really fine detail, that's the kind of expertise that I bring.
By the way, dear audience, if you go looking, you'll find, if you type in Peter Tuthill, there's all sorts of images. Look up WR104. Is that the one with the different rings around it?
WR104 is good for hypnotizing your granny. It's a sort of a spiral that goes around and around in a very hypnotic...
And what's the one that had the pulses every 7 years or something?
Yeah, well, annoyingly, that's called Wolf-Ray 140, not 104.
Okay, so let's bring our second person. Remember, we're talking about getting to the nearest star in a couple of decades, not in thousands of years. Dr. Boris, tell the audience who you are and so forth.
So I'm Professor Boris Kuhlmey, also with the School of Physics at the University of Sydney and the Institute of Photonics and Optical Science. My background is more metamaterials, photonics, lasers, and so I work on the sail aspect to send a craft to the nearest star.
And coincidentally, we just happen to have a picture. So Australia's way down there in the bottom. And here, so what are we looking at on this wonderful picture here?
So we are looking at a picture of Earth where Australia is in the center here, and a very powerful laser beam, that's the green bit here, shining to a sail that is in orbit.
Is that the sail?
That is the sail. So we have here a large sail, and in the middle
there's the whole thing is a sail.
The whole thing is a sail.
The whole thing is a sail.
And here you have the payload, which would have a very small camera and enough electronics to stabilize and to send back pictures all the way back from 4 light years away.
4 light years is the nearest star.
4.2 light years, yes. It's a very long distance, and it's a very small craft to be sending back data so far.
Hang on. So how big is the payload? Is it like a centimetre or 10 centimetres or a kilometre?
So to send it to the nearest star, you gotta really go really fast. It's 4 light years. If you want to be there within a lifetime, about 20 years, well, plus the rest of the scientific program. If you want to be there in about 20 years, you need to go at 20% of the speed of light.
20% of this, we can't even do 1%, which is 3,000 kilometres a second. The best we can do is 30 kilometres a second, which is 1/100th of that again. So you want to crank up something to 1/5 of the speed of light.
That's right.
And so the payload is how big, sort of?
So to get to that speed, that kind of speed, we have to accelerate very hard, and for that we need to have a mass as little as possible.
Yep.
And so the ballpark figure that people are looking at is about a gram.
A gram?
It might be 10, it might be 3, but it's of order a gram.
You got to have a radio transmitter that can punch a signal back 4 light years.
That's right.
And it weighs 1 gram. What about the battery for it?
So the battery would be most likely be a plutonium radiothermal source. And it wouldn't be a radio that would be sending back. It would be a laser, because you can direct that much more and keep the energy targeted to the Earth.
Right. But it'd take 4 years to get here.
Yeah.
And so the gram would be maybe the size of the tip of your finger or something.
Probably a little bit bigger. We're thinking like a big microchip. A microchip is very light and can do a lot of things. You can put optics on it. You can put electronics on it. So the probe, the intelligence and the sensors, all that would just be a chip. and the rest around it would be the sail to accelerate it.
Okay, you mentioned the sail. How big is this sail?
Details will emerge when we understand things better, but the ballpark figure is 10 square meters, so about 4 meters diameter. It's quite small.
Is that all?
That's all, because we want to keep the weight small.
So then you've got to hit it with a laser.
Very powerful.
How powerful is very powerful?
100 gigawatts.
Hang on. Australia's total capacity, if everything is running flat out electrically, is around 60, 70 gigawatts.
Yep.
And you want to put all that into a beam a few millimeters across.
Well, a few
More
meters
than that.
across. A few meters
By
across.
the time it gets to the spacecraft.
Even on the laser on Earth would be very, very large, because we have to beat the diffraction. So we have to shine the laser on the probe that is so far away. We have to have a very, very large laser. We're talking about a kilometer in diameter.
Sorry, the laser?
The laser itself on Earth would be basically a 1 kilometer diameter laser.
What, like the glass at the front would be 1 kilometer across?
It would be multiple little telescopes, basically, all joined together. But overall, it would be a kilometer in diameter.
Now, we should point out, Peter, that your job is to make sure that when a thing gets there, it's got a bus stop somewhere to land, and we'll talk about your role in a little while with your telescope, I'm guessing, in orbit. That's where you normally have your telescopes?
Yeah, the telescope I'm building will be in low Earth orbit. It's not going to fly to Alpha Centauri, unfortunately.
So you're the second part of this multi-part. Well, there's many parts to it. So your part is called what watch, is it?
Yeah, so the initiative that funded the program that I'm working on is called Breakthrough Watch.
Breakthrough Watch, and your Breakthrough
Starshot.
Okay, so they're two of possibly more branches, but that's all we're talking about today. So what do you got for Breakthrough Watch?
Well, we need to talk to each other, because Boris needs to know that there's a worthwhile destination at the end of this ride, right? If you're going to spend sort of several billion or trillion dollars on a technology to fly to Alpha Centauri at these insanely high speeds, there better be a destination worth getting off the bus at the far end. We need there to be a habitable planet or something really interesting, so that it make the journey worthwhile. We're going to beam back some photos. We maybe even physically there, so we could even drop some technology. But you really need this whole enterprise to have a destination.
Right. So, and that's called Alpha Centauri. Now, I remember when I was very young reading science fiction, and there was a story about somebody going through the ruined city of New York, and they left the basements and went up to the sky to stare at Alpha Centauri. And I worked out they'd be better off going into the basement and trying to stare through the bulk of the Earth, because you can't see Alpha Centauri from that far north in the northern hemisphere.
Unless the apocalypse has tipped the orbit or something.
Good point. And there have been movies about that.
Yes.
So take us through. So Alpha Centauri is not just a star with nothing. Take us through what is actually what we think is there now.
Well, so what we need to be there, we know astronomers pretty much know what Alpha Centauri looks like. It's a star. We can characterize it very, very well.
But there's
and we
three of
don't
them?
need to fly to Alpha Centauri to study just another star.
Ah.
What we're interested in going to would be a habitable planet, would be the ideal bus stop to get off there, because Alpha Centauri is only 4 light years away. So
it's the closest one at the moment to us of any star type thingy.
Yeah, it's a triple system. There
It's
are
a triple system.
3 stars in the system. Alpha Centauri A and B are a very close binary.
So there are, and by the way, is it true that 40% of roughly everything you see with the naked eye at night is a binary?
Yeah, that's
Ballpark
probably
figure?
about right.
Okay, so you've got 2 stars going around each other.
And then there's a distant third one, Proxima Centauri, which is actually the closest star to Earth, and that's very, very far away from this close pair of sun-like stars.
So there's when you say sun-like, you mean there's a whole list of stars which start off at O and end up at...
Yeah, you have dim, cool ones, and you have powerful, hot, fierce, ferocious blue ones, all the way through this scale of stars. And the dim red ones, and Proxima is one of those.
Proxima is a dim red. Yep.
It does host a planet in the temperate zone, so that planet could potentially have, the right mix of radiation coming from the star to keep it warm, but not to bake it too hot. So it's the sort of Goldilocks zone.
But isn't that frustrating? You said that there are 2 stars like our sun. Are they called G stars?
That's our star is a G star.
Yeah, so they're kind of close to a G star.
Mm-hmm.
And frustratingly, the planet is not going around either of those.
The one we know about.
The one we
Yeah.
know about.
Yeah, the one we
Because
know about.
the one we know about is going around Proxima, which is a red.
It's a red dwarf. Yeah, it's a red
Now,
dwarf star.
I remember you telling me in the corridors that you think that red dwarfs are like cockroaches. They're all over the place, and you don't want them because they mess up the interesting stuff you're looking for.
Yeah, well, that's a little bit of a biased view from my personal sort of astronomy research, but yeah, they're very, very common. Red dwarf stars are the commonest kind of star, and they're many red dwarfs very close to Earth, and in fact, the closest star, not surprisingly, is a red dwarf. But what we're interested in as scientists is we're interested in trying to find really a distant biosphere. We want a habitable planet.
A biosphere.
Yeah. So
Bio
that's the big
life.
excitement would be a planet where potentially there could be a flourishing, habitats. There might be exobiology already active there.
So exo means out of the solar system, bios, life. And so you're saying, I think you said that this planet is you mentioned the word temperate zone. Does that relate to the so-called Goldilocks zone, whatever that is? Can you explain that?
Yeah, it's often used in the same context. So when the planet receives just about the right amount of radiation from its host star to stay warm, but not really get baked and then turn into a ball of lava, then you have a temperate zone orbit. But we only have one example where we know life is flourishing. It's here on Earth. And so just as scientists, when we look out into the universe, because we've only got the one data point to spring from, we sort of look for life as we know it, to take a line from Star Trek, not life not as we know it.
Ah.
So life not as we know it, if we found life, for example, on Proxima Centauri, it's a red dwarf, the orbit's very different, everything about this system is very different from the Earth and the Sun. So that would be kind of like an example of life not as we know it. And
Right.
we don't know any examples of life not as we know it because we've only got the one here to go from.
Although the exobiologists do tell us that there's 5 bodies of water underground in our solar system, 1 on Mars, 2 on moons of Jupiter and 2 on Saturn. So potentially, but that's different from there is.
Well, yeah. I
Yeah.
mean, astrobiologists, people who study life beyond our biosphere
Oh.
out in the universe, they're super interested in places like Enceladus
Yes.
and many of the moons around both Saturn and Jupiter, because they do have subsurface oceans. And that would be another example of a habitat where it will be life not as we know it. But the excitement around Alpha Centauri and my mission is looking for life as we know it. So if we found an Earth-sized rock in about a 1-year orbit around either of the 2 stars in the Alpha Centauri system, that's kind of the jackpot. That's the holy grail of my field.
Oh.
That would then be a true Earth analog. That would be a planet like Earth around a star like the Sun.
Just a little diversion here. We've discovered about 3,500 or 4,000 or 5,000 planets. Do any of them yet fit into that category?
There are some that are getting more and more close.
Right.
There's actually an index that astronomers have for, it's basically like a real estate agent index. You've got an ocean view and you've got a nice, quiet street. So we've sort of got the same thing going on in astronomy. We have different metrics that we try and meet for how nice is it going to be to go on holiday there? Is it going to be nice and temperate? Could there be an ocean that goes surfing in? So we've got this index, and that index, because we're not now looking around one of these red cockroaches, we're looking around a sun-like star.
Yeah.
And we're looking for an Earth mass object in a 1-year orbit, that would tick lots of those boxes
Right.
straight away.
But we haven't got that, though. We've got something going around Proxima Centauri, which takes many, many thousands of years to orbit around the other 2 that are going close. So that's a red dwarf. And what's the rock that's going around it? Is it a rock? Is it a gas? Is it close? What do we know about it?
The Proxima planet?
The Proxima planet.
Yeah, it's kind of a rocky, it's believed to be a rocky world. So it's got the right mass range to be, so it ticks one of those boxes, right? We don't have a gas giant. That would be life not as we know it. Maybe there are floating intelligent clouds in,
I believe in them because I've read science fiction.
Sci-fi books when I was a kid had
Yeah.
all kinds of wacky ideas for what life could be, and that's great. It's good to speculate. But if we're looking for an Earth mass object, then we'd have a rocky world. Astronomers are a little worried or skeptical that these planets around red dwarfs, which we've found quite a few by now, because they're not as we know it, in the not as we know it category, that it may be more difficult for biospheres to be prolific there, because the host stars themselves even though they're dim and red and they don't burn very, they really husband their fuel over long periods, you'd think they'd be really nice, stable places for life.
I thought they'd be stable.
But it turns out that red dwarf stars can kind of turn a bit nasty for the planet.
What? They can have hissy fits.
Yeah, the planet has to orbit very close to stay warm because it's a dim star. And when you orbit very close, you're kind of prone to lots more space weather coming from the star. And that space weather, they're not nearly as stable as you might think. They kind of throw off prominences and sort of solar flares.
Even though they're a little red cockroach, red dwarf.
Yeah, so there may be examples where they're nice and stable, but many red dwarf stars are probably not the nice place to go looking for life.
And so what's the thing that you want to put into orbit, and is its name in any way related to the little logo you're casually wearing? Take us through it.
I'm wearing my branded merchandise today, Carl.
Excellent.
The Toliman mission is my small space telescope. It's got an aperture of about 12 centimetres. It's about this big.
Yeah.
It'll be, in fact, Australia's largest science-based space telescope when we launch it, hopefully on a timescale of about a year.
So 2026 sometime.
Yep, that's the plan. And the idea is that we want to answer this question. Is there this potential little island refuge around our very nearest sun-like stars? So is there a habitable world, or at least a temperate orbit world, ideally a rocky mass planet, like a one Earth mass, not a big gas giant planet? And so that's an embarrassing question for an astronomer, because this is our nearest neighbor. It's like, we've been in the neighborhood for quite a while now, Carl, and we don't know anything about our nearest neighbor. It's kind of like, a little bit rude, I think. You haven't even chatted over the fence. So what we need to do is we need to launch some kind of technology which can either rule out that there's a planet there, or detect whether there's a planet around A or B. We'd be happy with either. But as it stands, despite these 4,000 planets you talked about, astronomers announcing all the time, we don't know much about our nearest neighbour. So
really?
We're trying to patch an embarrassing hole here.
So we know for sure that there's one rocky thing around Proxima, which is the red dwarf. Does it have an atmosphere? We don't know that yet.
Probably not. The Proxima planet, because of those conditions I mentioned earlier. It's not easy to maintain an atmosphere.
And in what ranges will your telescope be looking? Optical and infrared or ultraviolet?
Telescope I'm going to fly will work in the optical, basically green. It sort of accepts green light, a band of light around the green part of the spectrum. And we're trying to detect whether the planet is, if there is a planet there, it will cause the star to wobble a tiny amount on the sky. It's an infinitesimally small signal. But as the Earth goes around the sun also wobbles around a common center of gravity. So the way physicists think about it is the Earth and our sun have a common center of mass. It's a couple of 100 kilometers off the true center of the sun. So there's a point a little tiny bit away from the center of the sun, because the Earth is so light, it pulls the sun around this tiny little loop. So that's the signal that we're looking for with my mission, except, of course, we're looking at the Alpha Centauri star.
So you're looking at it wobble as it goes. You're looking for, when you observe Proxima over a period of time, you're watching for it to wobble. And is it in an elliptical, is it in an equatorial or polar orbit, and how high up is it?
Well, we don't.
Or will it be your spacecraft?
Oh, the spacecraft.
Yeah.
The spacecraft will be in what's called a sun-sync orbit, so it'll go over the poles. It'll it's not an equatorial orbit. It goes over. Yep, and it follows the line of the sunset around the world.
Ah, wow. Okay, so this is the bus stop we want to get to. Getting back to you now. So I'm kind of guessing that when you announced your desire to be involved in this, they didn't immediately send a big bag of gold to you.
No, they did not.
So are you being funded by them at all, or are you doing this?
No, I am not. We got some initial funding from the University of Sydney, from the Physics Foundation. That got us started, and now I'm continuing with no funding. Luckily, I'm a theorist, so pen and paper doesn't cost much money, and there's a lot to be explored there before we can do any kind of experiments anyway.
Oh, the experimentalists hate the theorists because they come up with so many theories each time they have a cup of coffee. Okay, so
That's right.
So what sort of theoretical things are you looking at with regard to a laser beam with more electrical output than Australia, with an aperture of a kilometre-ish, trying to pump the signal onto a 10-metre across sail, which is relatively easy-ish if it's in orbit going around us pretty quickly. But what about when it's out past Mars or past Jupiter or even past the Voyager spacecraft? The Voyager spacecraft have been going for 50 years, and are they the currently most distant objects that we've launched?
And they're still getting data, which is amazing.
Yeah, but at the speed at which they're travelling, to get to Centauri, if they were aimed there, would be 80,000 years.
That's right.
And you're cutting it from 80,000 down to 20. So,
That's right.
Tell us more about what sort of theoretical things bother you at night as you sit there with your pencil and paper.
The one of the greatest difficulty is, well, there's many difficulties in this project. There's no laws of physics are being broken, so it's all possible. It's just very very difficult. And so the one difficulty I'm working on is how to keep the sail within the laser beam. So the laser is pointing at Proxima Centauri.
The laser's on Earth, which is rotating.
That's right.
So you've got to keep on swiveling it.
So you swivel it. You don't actually swivel the laser. You adjust the phase, but the end effect is the same. You adjust. You compensate for the rotation of Earth to keep the sail inside the laser. We can't have thrusters on board. That adds too much weight.
It weighs a gram.
That's right. So we can't add little rocket engines. They're just too heavy. So we have to have the laser forces themselves creating this stabilizing force, and that's not easy at all. And you can't just readjust the laser as you go, because the time for a signal to come back to the laser is more than a second or even 60 seconds by the end of the acceleration phase. So you don't have time to adjust. So it's all gonna happen on the sail. The sail needs to have those restoring forces that push it back towards the center of the beam. And that's very much an optical problem.
Wow.
And then it also needs to have stabilizing torques, and even worse, it needs to have some kind of, there is no friction at space. So if you have a restoring force, it's like a pendulum or a mass on a spring, it starts oscillating.
Right, because you mentioned the acceleration phase. So is the idea that you would accelerate it a lot for a brief period of time,
right.
Like a second or a minute or an hour?
About a minute, about a few minutes.
For a few minutes, you'd be pumping 60 gigawatts, 100 gigawatts at it.
That's right.
But then, what if it's just a little bit off to one side and it misses the target by stellar diameter?
Yes, indeed. So we got to keep the laser pointing very, very precisely, which is a huge challenge. It's especially a laser that big, but we know it's possible. It's just a really, really huge challenge. And then we got to keep that laser inside the beam with all those restoring forces that we work on. And we got to make sure that it doesn't oscillate, so we got to somehow attenuate those oscillations. Otherwise, it will indeed go off course. And if you don't do it right, well, you might miss. It could be the difference between being as far from the Earth as the Moon, or as far from the Earth as Jupiter. And if you're on Jupiter, you will see a little blue dot. If you're on the Moon, you will see the beautiful Earthrise that we have a picture of.
So let me get this straight. The acceleration is done only once?
That's right. The acceleration
only once.
Only once.
So once it's on its path and it's heading out past Mars, etc., you don't tweak it a little bit?
No, you just stop the laser, because then it's so far that the laser can't focus on it anymore. So you would not accelerate it anymore. So you have the laser is on 100 gigawatts for about a few minutes, then you turn it off. And then you just let it cruise until it gets...
And then you do the same to another space. So how many of these would you have? Like 1 or 10 or 100?
A lot.
Like thousands?
Probably 1,000, I would guess, because the really expensive part is the laser. Then the cell itself is much more manageable. Especially, you would work to have some kind of mass production line, automated, all that. So the laser is the expensive part. The cell is not so expensive. But the failure rate is expected to be high.
Failure in terms of damaging the spacecraft, or going off course, or both?
Both. So you only have some control over the spacecraft. You will need the data from Peter to know exactly where the planet is to aim there.
Yep.
And there's dust in space. There's dust and protons in space. There's very, very little. But when you go over 4 light years, it does accumulate. And so you design this craft so that the dust impacts is not creates as little damage as possible, or build in plenty of redundancies, but inevitably a lot of them will fail. So if you send, say, 1,000, you expect maybe 10 or 20 to actually arrive on destination and be able to still take pictures and be in the right spot.
And there's no concept at all of trying to tweak the orbit or the path later with...
Not really. So there is an option of doing very small tweaks in rotation and so on. You have to rotate the camera to aim at the planet anyway. You have to rotate the laser to send the data back on Earth. That would actually be also done with photon forces on board. Very, very, very slow because the forces would be tiny.
The photon forces from Earth?
No, from the sailcraft. So on the sailcraft, you have this little plutonium battery, basically.
Oh, you have a plutonium battery.
And it's very little power because it's very light. But the power emitted by that can be directed, in principle. This is all, very, very theoretical at this stage. And so you can use that to change the attitude, change the orientation of the craft a little bit. But so that's about all you can do.
And there'd be like a reverse thermocouple effect where the plutonium would heat up one bit of wire.
Yeah, so you can do that, but in fact, for the couple, for the torque, for the forces, you may as well just use the heat that is radiated directly. If you modulate the heat that is radiated,
of course,
you can just direct create force from that.
Wow.
They're tiny forces; they're really tiny, but they're enough.
So, what's a rough ballpark figure, bearing in mind that the world, Australia's GDP is $1.5 trillion a year and the world GDP is $100 trillion. What's the rough ballpark figure for building this big fat laser and all of the spacecraft?
So if you wanted to buy the laser now with existing technology, which would still need to be developed further, but if you take the cost of things as they are now, you'd be talking about $1 trillion.
Wow.
Which no one wants to spend, right? This is not the kind of scale that we do science on. But there is such a thing as Moore's law for lasers, that the price of a coherent watt coming out of a laser halves about every 18 months or so. And so after 30 years...
Really? It halves every 18 months?
Also, I can't remember the exact number, but it's of that
varies.
order. So it's an exponential decrease in cost, like computers,
Yeah.
And so in 30 years, this 100 gigawatt laser might be not $1 trillion anymore, but more a few billions. And then we're in business, right? Big science projects, they are of order billions of dollars.
Wow. We're coming to the end, Dr. Peter, Dr. Boris. So how, if people want to get involved with this, how can they contact you, Professor Peter, to get involved and become your student?
Well, Toliman's got its own website. You can just search for Toliman.
Toliman. Right. And Professor Boris, or Dr. Boris, how can people follow you and your fine work and help you write things on paper?
So our work does not have a current website, so email is probably the best. But if you want to get involved, I think there's two ways. The first is study physics. That's how you get into these fun things.
Yep.
And the second one is, you can always fund me.
So can you spell your surname so they can find you at the University of Sydney?
So my first name is Boris and last name is Kuhlmey. Kuhlmey.
Look, thank you ever so much for coming on board for Shirtloads of Science. And so this is a long-term project that some of the younger people today might actually find happening in their lifetimes.
That's right. I like to compare it to LIGO. 30 years ago, detecting gravitational waves seemed like science fiction. Now we do it. And I think this is a kind of similar kind of scale.
Okay, thank you very much, guys.
Thanks, Carl.
Thank you.
Thanks, Carl.
Shirtloads of Science is washed, spun and aired by the University of Sydney.